So in this lesson, we're going to learn how to graph parabolas, and we're going to do this using transformational form, which is very useful for all kinds of different functions. But then we'll also look at a quick shortcut that works only for parabolas. But first, let's take a look here at a little question on the patterns that we've done before. Again, your midterm and final will have some multiple choice questions on it, and these kind of questions help you look at maybe quick ways of doing this. So which of the following relationships describes this pattern? What we can see here is that the pattern is decreasing in value. If you look at the values here, you can see that they're getting smaller and smaller. And so right away, I know that my common difference has to be negative, and the common difference is showing up next to the n in these equations. And so these two, c and d, are increasing functions, whereas a and b, because of the negative sign, are decreasing. And so we just have to decide now between a and b, and we can certainly do this problem out. But sometimes you can do it a little quicker if you, for instance, set n equals to 3. We know that t of 3 is actually negative 3. And so what we can do now is we can plug in to our two choices and see if we get this negative 3. So when I plug in n equals 3 to the first choice question, or answer A, we see that's negative 6, which is not the value that we want. We need this negative 3. And so to double check, if I plug in this value of 3 for n into the equation in B, what I have here is negative 6 plus 3, and that does equal negative 3. And so what we have here is the answer of B. So that's just a quick way of showing you that you don't actually have to do the pattern. You don't have to do it out to find the equation of it. We can look at another way of doing it. Here's another example of a pattern. Find the 62nd term of this pattern. Now this one is a little bit different. You're not going to guess and check this. You're not going to finish this pattern off. Here the quickest way is to get the equation. And so since this is a linear equation, and we know that because the common difference is on the first level, we can go and that looks terrible, sorry. We can go and use our values to find the equation. So Tn equals T1, which in this case is 1, plus n minus 1 times the common difference, which is 8. And so last class we talked about how you would have to multiply this 8 out. Okay, and I'd certainly still want you to do that if I asked for the equation. But here I'm just asking for the 62nd term. So what we're trying to solve for is when n equals 62. So why bother simplifying it now if all I want is a numerical answer? And so what I have here is the 62nd term is going to equal 1 plus, this would be 61 times 8. And so 61 times 8 is 488 plus 1. This gives me 489. And of course we see that's answer A. So last week we talked all about patterns. We've learned that a linear pattern has a common difference on D1. We just used that in the last one. And its pattern can be represented by the equation Tn equals T1 plus n minus 1 times D. We saw that the quadratic pattern has a common difference on D2, and that common difference always equals 2a, where a is defined in the equation an squared plus bn plus c equals Tn. Sometimes you'll hear a linear pattern called an arithmetic sequence, and that just is a different term to mean the same thing. So we're going to graph these parabolas, so let's graph. And every time I say that, I think of David Bowie's song, "Let's Graph." anyways, that's why that's there. It's weird, I know. In any case, what we have here is we see that quadratics don't have a common difference on the first level, and therefore their graphs aren't going to be straight. They're going to be curves. And so if we look at the simplest quadratic ever, this is the function f of x equals x squared. Okay? So I ask you to think about why this would be the simplest quadratic. Remember that a quadratic has the form y equals ax squared plus bx plus c. And so in order for this to be a quadratic, we definitely need this a term. And so let's put that as a 1. That's the simplest number. You can see the a value is 1 here. And then the b and the c values could be 0, and that gets rid of those. And so then what happens is we're left with y equals x squared y equals 1 x squared. And so what we have now is an equation that we can get a pattern. Now, you can see here all the tn values are just the squares of the n values. We're not going to use n and tn anymore, because when I want to graph something, I want numbers in between these 1 and 2 and 2 and 3, etc. X could be 2.72, x could be negative values, x could be 0. And when we're talking about a pattern, it doesn't make sense to talk about the 0th term, or the negative 2th term, or the 57.26th term. So we don't need, or we will need a decimal placer, so that's why we're going to use x and y. So if we take a look here at this pattern, what we get is this equation. Let me just get rid of this stuff. So what we have here is the y equals x squared table, and this is showing us that what we did here was we picked any x values we wanted. I picked negative 3 to 3, and that's commonly what we'll use. All of these kind of functions, the quadratic or cubic, or y equals x cubed, these are called polynomials, and polynomials usually have functions, usually have their characteristics happen near the origin. And so we want something near x equals 0. So we just picked a sample here of data around the origin. And so to get the y values, I simply square these. And so that's how I'm getting this. And this table is very important. And so what we can do with this now, all of our graphs are going to come from this. So when we graph this, we see that there's some characteristics. First of all, this type of curve, a quadratic curve, is called a parabola, as you see here. And this parabola has some certain characteristics. And so these characteristics are things like the domain and range. Now the domain is XER, and what that means is that you can have any x value you want and plug it into this equation, into our equation y equals x squared. This equation allows for any x value, negative values, 0 values, positive values, decimal values. All of the numbers that we're familiar with are real numbers. However, the y values, which is what the range considers, you always read the graph from smallest to biggest. And so down here, there's no graph at all. The graph begins at y equals 0 and goes up. So we use this term here, y contained in all the values from 0 to infinity. And so the square bracket indicates that the 0 is included. Okay, so you can see the 0 is part of our table of values. And the infinity is a round bracket beside the infinity because we can never get to infinity. It's not included. Now this type of notation here is called interval notation. and that's the kind that I'll use. You may also use this kind, which just simply says y is contained in, y is greater than or equal to 0. And that might seem simpler, but it's not as useful later on in other math courses. So there's another characteristic that we need to look at for this graph, and this is the axis of symmetry. This is the line here, and you can see it was already highlighted on my screen. But this is the line that the graph flips onto itself. Okay, so I could take this branch and fold this page over along this line, and it would fold onto that. And so this is the axis of symmetry. It's x equals 0. And both the axis of symmetry and the range have to do with the vertex. The vertex is the most important point of a quadratic. It's where the quadratic goes from, in this case, decreasing to increasing. It's also, in other words, it's where the two branches meet. And this is the most important point, as we'll see later on. So if we take this base graph of y equals x squared, the simplest quadratic, we can reflect this graph, we can stretch this vertically, we can slide it horizontally and vertically. And what this does, these are called transformations, and this changes the graph. And so if we look here, I will shorthand these to be the reflection, the vertical stretch vs ht and vt. And they show up undone in the equation. It's called transformational form. So this is the general form here. That's what we've talked about, ax squared plus bx plus c. But this is transformational form, so it's another way to represent the quadratic. And we would look at this in terms of math being, again, ways to represent different ways to represent the same information. And so I have a quadratic that has a form of ax squared plus bx plus c, but now I also have this new transformation. So I'm going to take a moment here and go beyond the PowerPoints just to show you how these transformations show up undone. So if I take a look at this equation, this is a new pattern, this is a new relationship. What I can do here is this is y minus 4 equals x squared. And so I can take this now and look at what this does to the old graph. So first of all, this says y equals, as I add 4 to both sides, this is y equals x squared plus 4. And so what this x squared was, this is very important, this was my old y values. And what I mean by old y values was the values that we had from the original graph, y equals x squared. And so you can see there's my old y values. This x squared is my old y value. So this new equation tells me to take the old y values, and add 4. So I'm going to do that. I'm going to take my table here, -3, -2, -1, 0, 1, 2, 3. And there's my old y values. Now what I'm going to do is then take my new graph, new table, and I'm going to do nothing to the x values. But here, to get this new relationship, as I said earlier, we have to take our old y values, the x squared values, and then add 4 to them. So this is actually going to be 13 for the 9. 9 plus 4 is 13. 4 plus 4 is 8. 1 plus 4 is 5. And 0 plus 4 is 4. And so this is my new table of values. And so when I plot this, what I see here is that I have x equals -3, y equals 13. And what would end up happening here is I won't plot those y values, but it ends up being like this, where at this point, it should be the lowest. That low value is actually now, that vertex is now 0, 4, which makes sense if you look at the old y value of the vertex, it was 0. Now it tells us to add 4 to it. So we've slid this graph up. This is a vertical translation. Now I want you to notice that the vertical translation started here, and this is part of transformational form. It started with -4, but what actually happens is it's a vertical translation of +4. Okay, so that's part of the reason why everything kind of shows up backwards. I'll do another example. So if I take an equation of 1/2y equals x squared. Again, what this means is to take my old values of y, and multiply both sides by 2 here, take my old values of y and double them. Even though originally it looks like I'm taking half of my y values, but you have to remember that this is the old y values. So again, I'll take my old table values, -3, -2, -1, 0, 1, 2, 3, and 9, 4, 1, 0, 1, 4, 9. I'll take these values. I'm not doing anything to the x values. But what I do now is I'm taking the old y values and doubling them. So this will be 18, and this will be 8, and this will be 2, and this will still be 0, 2, 8, 18. So again, you can look at the graph a little bit better probably than I can. But what happens here is that if the old graph looks like that, so here's y equals x squared, then the new graph now has doubled the y values, which means it's going to be narrower. And again, I'm exaggerating this a bit, but you can see that those branches have moved in. Okay? What's important here again is that it looked like it was 1/2, but it actually ends up being a vertical stretch of 2. Okay, you can imagine that if I had a piece of Play-Doh and I stretch it vertically, I take the Play-Doh and I stretch it, it gets thinner, and that's what's happening to our parabola. And now I can do one more. This one's a little bit confusing, a little bit more confusing. Let's take a look here at y equals, let's say, x plus 3 all squared. So now what I have here is I'm adding 3 to all my x values. And so what happens here is, again, I take my x and y chart. All the quadratics come from this basic relationship. And now what I'm going to do is I'm going to look at not changing the y values. So I want to know now which x values will give me, which new x values will give me these y values. So you don't have to do this every time. I'm just showing you an example here to try and make sense of what this relationship is going to be. So if I take the y value of 9, anywhere I see a y value, I'm going to plug in 9. And now, to undo what's being done, I'm going to take and square root both sides, and that will undo this square. And the square root of a square is just the original term. And then here I have the root of 9, which is plus or minus 3. Now there are two answers. The square root of 9 asks what number multiplied by itself gives you 9. Well, 3 times itself gives you 9, but so does -3. And so there are actually two equations here. If I subtract 3 from both sides, I'll get plus 3 minus 3, so I get x equals 0. Or I'll get x equals minus 3 minus 3. And so here I get x equals -6. And so this is the -6, not that it matters. This is the -6 and this is 0. In fact, I can continue doing that. I can take and say, well, what happens if y equals 4? What's the new x value that would give me y equals 4? And I square root both sides. and I get plus or minus 2 here to equal x plus 3. And so when I subtract 3 from both sides, I get negative 3 plus or minus 2. That's usually how we write it. And so this means negative 3 plus 2. That gives me negative 1. Or x equals negative 3 minus 2, which gives me negative 5. And so you can see that our values here, and we continue this, negative 6, negative 5, they're all decreasing by 1. And that's because we won't have a vertical stretch. Sorry, a horizontal stretch. So this is the new table, and when I go and graph this new table, this equation was y equals x plus 3 all squared. What happens is this plus 3 actually moves the vertex over to negative 3 comma 0. You can see that right here. And so the graph looks the same in terms of the same shape, but it's been slid over horizontally. And so this ends up being a horizontal translation, not of plus 3, but of minus 3. So that's why when we talked earlier about the transformations, if I can go back to this slide, we see that they show up undone. So I always say that transformational forms like the Bizarro world, those Seinfeld fans out there, Bizarro world was where Superman was weak, and in the daytime it was dark out. Everything was backwards, right? I wasn't funny at all in Bizarro world. Everything's the total opposite of what it is. And so what we can see here is that when we have transformational form, we can get those transformations as long as we recognize that they're undone in the transformational form equation. So if I take a look at this function here, we're going to graph this now. Now first of all, what you need to recognize is that this is a quadratic. And I see that it's squared, and that means the base equation that I'm using is y equals x squared. That means I'm going to use that same table that we were just using, 9410149, and we'll use the transformations of that. So the first question you ask yourself is, what are these transformations? So I don't see that there's a reflection, and the reflection would show up right here. It'd be a negative sign, and that negative sign would make the y values negative, and that would flip the graph upside down. But we don't have that here. We'll have that in later examples. We do have a vertical stretch. The vertical stretch shows up right here. It's a 1/2 in the equation. But how do I undo multiplying by half? Well, I divide by 1/2, which is the same as multiplying by 2. And so my vertical stretch will be a 2. Then I look for a vertical translation, and I see that there is one here. We have a vertical translation right there. It's a plus 3 in the equation. That shows up on the graph as a minus 3. And the same thing for our horizontal translation. We have a horizontal translation of minus 1. Or sorry, a horizontal translation of 1, because in the equation it shows up as a minus 1. And here it'll be a plus 1. And so now we can get what's called a mapping rule. And so what the mapping rule tells us is to take the old table, so the old x and y table, and since this was the quadratic, we're talking about the table that 9410149. We take those values and we do these transformations to them. So you can see that I take my x equals, or my x values I should say, and I add 1. I take my y values and I multiply them by 2 and subtract 3. So this is the mapping rule. This tells me how to get my new table. Okay, so we take the old table of values and do what the mapping rule says. I'm literally going to plug in x equals negative 3 into here, x equals negative 2, x equals negative 1, 0, 1, 2, 3 into here, and same with those y values. And when I do this, there's the old table, and I plug in these old values into the new ones, and you can see that I added 1 to all the x values, So instead of -3, I now have -2. And to the y values, I plug this 9 right in here. That would make it 18 minus 3 gives me 15. And so you can see that I did that for all of these y values. 4, let's plug in the 4 right here. 2 times 4 minus 3, that's 8 minus 3, which is 5. And so now I have a new parabola. And that parabola, when I graph it, this is the blue one, this red one here is just for reference. This is just the y equals x squared. But you can see that this blue one has been stretched. It's now narrower than the red one. It's also, for instance, this vertex is now moved over 1 and down to this new point. And so you can see here that the vertex is always the horizontal translation, comma the vertical translation. Now normally what will happen is we don't use 2 letters to represent variables, so the transformational form will look like this. 1 over a bracket y minus k equals x minus h all squared. And so what we describe here is the vertical translation and the horizontal translation as k and h. And so the vertex is always going to be h, because the x comes first, h comma k. So you can see here that my vertex, of course, shows up in my table, but I actually can look at this equation right away and see that the vertex is 1, -3. And so we can look at the characteristics of this graph, and we see that the domain is XER. Of course, that's always going to be the case for our course. There's not going to be a time where I'll ask you about a quadratic that doesn't have a domain of XER. The range will change, of course, and we do it the same way. We read from the top to the bottom. I see that the lowest point here, the minimum value of this graph, is y equals 1, 2, 3, y equals -3, which of course is my vertical translation. And then this graph goes up to infinity, and so I have to remember that there's a square bracket around the -3 and a round bracket around the infinity. And then we have x equals 1 as the axis of symmetry, because again, this is the line here that the graph would be reflected on. And that's always going to be the x value of the vertex. Now, I mentioned at the beginning that we could have this a shortcut to do parabolas. This doesn't work for every kind of function. This is what we're going to talk about here. Whereas transformational form works if you have a sine graph, if you have a tangent graph, if you have any kind of polynomial, if you have a rational function. We can use these transformations in any kind of scenario. All that changes is our base graph. So for instance, if I had a cubic, I'm not using the pattern 9410149. It's a cubic, so when I take x equals -3, I'll get -27. X equals 2, I'll get -8. And so that changes the pattern. But the transformations are done the same way. You just have a new base table. So what we are going to do now, though, only applies for parabolas. And so if I know the vertex, which again, we can figure that out very quickly just by looking at the transformations, what I can do now is I can follow the pattern over 1, up 1, which is what the old table did, over 1, up 1, from both sides, over 2, up 4, this is to get the old quadratic, over 2, up 4, and so these are the points here, and over 3, up 9. But now I've stretched this new parabola, and so what will happen here is that I'll take it and I'll say over 1, up 1 times the vertical stretch. Well, our vertical stretch was a 2. So from the new vertex, I'm going to go over 1 and up 2, over 1 and up 2, over 2 and up 4 times 2 would be 8. And you can see these give us the points that are on our parabola. And so this is a very quick way of getting the graph of the parabola. I will ask you to do transformations. I will ask you for mapping rules. But if I don't, and I just say graph this parabola, you can find the vertex and use that pattern very quickly. So here's a chance for you to try these. You can perhaps pause the this recording and try these. The answers are in the PowerPoint as well, and I'll go over them in a moment. So it's a good chance to press pause and then do those. Okay, so now that you've had a chance to do those, we'll take a look at the answers here. Again, what I do with this function here, it's in transformational form, and I can recognize that there's no reflection because there's no negative sign here. There's a vertical stretch of 2 because it was a 1/2 in the equation. The -3 indicates that there's a vertical translation of 3, and the -2 indicates that there's a horizontal translation of 2. Now, what happens here is that it gives us a mapping rule, and our mapping rule now is take the old x and y and map it with x plus 2 and 2y plus 3. And so you can see that's where these are coming from. And so when I do that, I get this new table of values. Okay, so again, I took the old x values and put them in here, so I added 2 to each one of them. I take the old y values, plug them in right here, and that means I double them and add 3. So that gives me 21 and 11 and 5, etc. And so what happens when I have this new table is I graph this parabola, and you can see that this is the shape. And you can see that the vertex is 2, 3, which we could have predicted just by looking at those values there. Again, they're backwards. So then we see that we go over 1, up 2, because the stretch was 2, over 1, up 2, over 2, up 8, over 2, up 8. Gets us to these points. So the characteristics of this graph are as follows. The domain again is XER. The range here, the minimum value is 3 to infinity. The axis symmetry is 2. Now the y-intercept showed up right in the graph, right in the table, 0, 0,11. And here are the answers to this one. This one's a little different because the graph has been reflected. We haven't seen a reflection yet. What happens here when I have a reflection is that it comes into the mapping rule on the y values. In other words, how do I undo multiplying by -2? I divide by -2. So another appropriate way to write that mapping rule, at least this part of the mapping rule, would be y divided by -2. We traditionally don't write it that way, but there's nothing incorrect about that. And so I see here that there's no vertical translation, that the horizontal translation is -1, and so now I get my mapping rule, and I get my new table, and my graph looks like this. You can see that the graph is pointed down now. The vertex is still predictable, -1, 0, because that's a -1, and there's my 0. There's no vertical translation. So my vertex here is -1, 0. The graph now goes down, and so my pattern is over 1 from the vertex, over 1 down 1/2. That's down because it's reflected. It's 1/2 because, again, it's the vertical stretch times that 1 value. And my vertical stretch here is 1/2. So this graph has been, it's wider now and pointing downwards. And that's going to change, that pointing downwards is going to change these values here. You can see that the range now is -infinity, because the graph starts down here, -infinity up to this maximum value of 0, and that's why the range looks like this. The axis symmetry is x equals -1, this line right here. Don't forget, it's never just -1. The axis symmetry is an equation, and so you you want to say x equals -1. And then your y-intercept shows up again in this table. When x equals 0, y equals -25. The last graph has a vertical stretch here of 1. You might say that has no vertical stretch. Well, if there's the vertical stretch of 0, then I have no y values, I have no graph. So we say that if the vertical stretch hasn't happened, then it's a vertical stretch of 1. And here's what this graph looks like. And you can see again, here's the values. Now notice that the y-intercept didn't show up in the table here. And so we can solve for the y-intercept by setting y equals, or x equals to 0. And so when I plug in x equals 0, 0 plus 6 is 6. 6 squared is 36. And now I can start undoing what's being done. I can divide by -1. And that gives me y minus 4 equals -36. And add 4 to both sides, and I get y equals -32. So this y-intercept is way down here. Don't get confused, this is just the program that I use. This is not, this y-axis here is not at x equals 0. This is actually at x equals -4. So this is -3, and -2, -1, 0 would be continuing to the right of that graph. So now we can go backwards. If I give you the equation, or if I give you the graph, you can find the equation. And so first of all, what we need to notice here is that it makes sense if we were given the graph to try and find the equation. We would find the equation not in transformation, or not in general form. We don't know how to do that yet. We'd find it in transformational form. And so remember that this is my vertex right here. And so here's my vertex, 1, -1. And so there's my h value, there's my k value. And so what I have to do here is I have to simply plug these values in. So I know right away that my equation is going to start with y equals, or sorry, 1 over a y plus 1, because it was -1, now it's going to be +1, equals x. This was a +1 here, so it's going to be a -1 in the equation. And so what I need now to figure out the 1 over a value is I need an x value and a y value. Well, I have one of those right here. I know that this point is 3, 1, which means that x could be 3 and y could be 1. And so I'm going to plug those values in. Now they are just x and y values. They are not transformations, so I don't change their sign. I have 1 over a equals 1 plus 1. Sorry, 1 over a times 1 plus 1 equals 3 minus 1 squared. And so this is 1 over a times 2, and this is 3 minus 1 is 2, squared is 4. And so to find the 1 over a value, I divide both sides by 2, and 1 over a equals 2. And this tells me that the equation of this parabola is 2 bracket y plus 1 equals x minus 1 all squared. Let's fix that in a second. Maybe. So this is a way for us to go backwards now. We can get the graph, and all we needed from the graph was the vertex and another point. And by the way, it didn't matter if you plugged this point in as well. This is very similar to what we had with a linear function. Linear function, we have y equals mx plus b. Once we found the slope, all we needed was an x and a y value to figure out this b value. And it didn't matter what x and y value we used from our last module. So let's take a look here at another way of going backwards. What quadratic function has a range of this and a vertical stretch of 4 and axis symmetry of -5? Well, these telling us information here about our transformations. Well, first of all, this is straight out, so I know my equation is going to be 1/4 y. And again, the axis of symmetry is always the x value of the vertex, so this will be x plus 5 all squared. And then this value of the range is always going to be the vertical translation. It's a +6 in the range, which means it's a +6 on the graph. It means it's a -6 in transformational form. And because this has been flipped, I can see here that the negative infinity is where the graph begins. I know it's been reflected. Okay. And then here's one. Question B is very similar to the last one we just did with the graph. It tells us the vertex and the other point, so I can right away know that my equation is going to look like this as I plug in the vertex. Remember that the signs of the vertex change because they are the transformations. But now I can plug in this x and this y, and I can look at solving for 1/a. And so -1 minus 2 is -1, squared is 1, and -9 plus 12 is 3. I divide both sides by 3, and I get a equals 1/3, and so my equation is y equals the new equation is 1/3 y plus 12 equals x minus 2 all squared. That's the only quadratic function that has that vertex, 2, -12, and that passes to the point 1, -9. Now we can use transformational form to solve the equation for a value of x given a value of y, which we couldn't do last week. And so here I have an example that says, given this parabola, what values of x happen when, or what values of x give us a y value of 2? And so what we can do here is we can see the parabola. Okay, we know we can quickly graph this. The vertex is 3, -6, and I'm going to go over 1 up 2 from the vertex on each side, and I quickly graph this. So I can see here are my answers. There's y equals 2, so the answers are x equals 1 and x equals 5. But I can solve this algebraically as well by plugging anywhere I see a y value. I'm going to plug in 2. So 1/2 2 plus 6 equals x minus 3 all squared. And so I can take this. This is 8 times 1/2 is 4. And what I can do now is I can solve this by square rooting both sides. I'll use a different stroke there. And remember that the square root of a number is always plus or minus. So here I have plus or minus 2 equals x minus 3. And if I add 3 to both sides, I get x equals 3 plus or minus 2. That means that x equals 3 plus 2, which is 5, or x equals 3 minus 2, which is 1, and that's what we have here, 1 and 5. So for the first time ever, we're able to solve a quadratic for an x value given the y value. However, it was in transformational form. That's the only way that we can do it. So let's take a look at another example here. Find the x-intercepts of the following quadratics. X-intercepts mean that we're trying to find the x values. given the y values. Again, the math comes down to me giving you one thing and asking you for another. So here I'm asking you what's the x value when y equals 0. And so you can solve this. Now I've done this out on the PowerPoint here, and I wanted to leave it like this. You could also obviously have a calculator with you, and so you could do this as -8 plus or minus, and then the square root of 20 is like 4.7 or something like this. And so you can put that in there, or you can leave it as the root of 20. I'm okay with that too. Yeah, the square root of 20 is 4.47. And so now you can get the two x values. If you do the same thing to this one, plugging in y equals 0, you end up with a negative under the square root. And that means that you cannot take this value. This is actually an imaginary number. We call this square root of -1i. We won't be dealing with this in this course, but I do want you to understand that this doesn't mean that you've made a mistake. The fact that your calculator can't get you an answer here, that there is no real answer. What this means is that there is no answer for this question. So find the x-intercepts of the following quadratics. This quadratic has no x-intercepts. And we can check that very quickly. We know the vertex is 1, 2. So there's the vertex. And it's not reflected, so it points up like this. And therefore it never crosses the x-axis, which is what this says. This says there are no solutions to this equation, which tells us that there's no solutions. There's no x-intercepts, I should say, to this graph. So don't ignore the negative under the square root. If you get one, it means that there's no answer to your question. So now we're going to quickly take a look at changing forms. We have a general form here that we've talked about, transformational form, but now you can also have standard form. And standard form is simply when we take transformational form and solve for y. So you can see I multiplied both sides by a and added k, and that's what I get here. Now these forms are good for different things. Transformational form is great for a lot of things. However, as you see down here, we don't usually write it in this notation. They're usually written in f of x notation. So we want y equals, like the general form. Now the general form is good for finding the y-intercept. Remember, if the y-intercept x is 0, and so that term's gone and that term's gone, all we get is y equals c. We can also find the x-intercepts and the vertex, but that's coming later. Standard form is good for nothing. We won't use standard form too often. If it's in standard form, I would suggest that you get it out of standard form. And one of the ways to get it out of standard form is to go to general form. And in fact, anytime we're going to general form, we're going to solve, or we're going to FOIL and solve for y. Now really, FOIL is an acronym that's not really useful, but it makes for a great joke, as you'll see. Really what we're doing here is we have to expand the binomial. And so if I take a look at foiling this out, FOIL means first, outside, inside, last. And what we have here is x minus 3 all squared. Well, what that really means, anytime I have a square, it means to take the value and multiply it by itself. And so we would recognize this as taking this x and multiplying it by both of these, and then taking this -3 and multiplying it by both of these. And so we do that, and that is the exact same thing as foiling. And so you can see here I took the x squared, x times x is x squared. Those are the firsts. The outsides would be x and -3, that would give me -3x. The insides give me another -3x. Excuse me, and the last give me +9. You don't have to remember this. This is exactly what I said earlier. You just take this x and multiply by both terms in here, and take the -3 and multiply by both terms in there. However, it's very quick for me to say that you forgot to FOIL, or you've been foiled again if you mess this up. Okay? A lot of times students will forget this, and they'll just write that this is equal to x squared plus 9. They just think that we can multiply, or that this square just goes on both of those terms. But really it doesn't, because you're missing this minus 6x. And so when you do that, I will say you've been foiled again. But hopefully it won't do that. So if I take a look at going to general form, here's an equation that's in transformational form. I want to put this in general form. So the first thing I look at here is what this squared means. It means multiplying x minus 4 times itself, which gives me x squared minus 8x plus 16. Now I'm going to solve for y, so I have to undo what's being done. I'm going to multiply both sides by negative 2. When I do that, every term on the right-hand side is multiplied by negative 2. And then to continue solving for y, I have to add 3 to both sides. When I do that, I get y equals negative 2x squared plus 16x minus 29. So that's not really useful for us right now. It will become very useful. But what I want you to recognize here is that this equation in general form and this equation in transformational form, although they look completely different, they are equivalent. They are the same thing. They are the different ways to represent the same information. We know a lot about this parabola right now. We know that its vertex is 4, 3. We know that it's reflected. We know that it has a vertical stretch of 2. We can find the range, the axis of symmetry. We can actually use this to find the x and y intercepts. And with this, we can't really do much. But this is the way we usually write functions. F of x equals negative 2x squared plus 16x minus 29. So our goal next module is to be able to take this graph, or this equation, and be able to get all that information that we could when it looked like that. And that's going to be complicated, so we'll leave that till next time. This time, what you were able to do is graph parabolas by understanding transformational form. You're able to solve a transformational form, an equation in transformational form for a y value and an x value. And now we're able to go from transformational form to general. So have a look at the homework and practice up, and hopefully that will make total sense to you.